And how do they work? Inhibit HIV. It's like this. If let me give myself a little, oops, yikes, that was not what I meant to do. There we go. If you got the viral RNA, and here's the 3' end, and you're trying to make a copy of it. So this is that sugar phosphate backbone. 1, 2, 3, 4 sugars. And then here's the 5' end. And suppose the viral RNA has a U and a C and an A and a C. And here's the DNA copy being made. It's going to have 5' end here, phosphate, sugar, phosphate, sugar, and then an OH at the 3' end. So this is going to pair with A, that's going to pair with G, right? So what's going on here? This is what reverse transcriptase does is it makes a DNA copy of the virus's RNA. So let's say we're in a snapshot here. This is the virus's RNA down on the bottom. Up on top, you're making a DNA copy. You're growing, adding to a 3' end. That's how all chains have to grow by adding to the 3' end. Well, so what's the next base you're going to add to the DNA? T, right? Because it's got to pair with that A. You're growing on here. So what you're going to do is if you have normally you'd add a T. Suppose instead of a regular T, an AZT ends up here. So this has got that strange N3 thing at the end, and it's got its 3 phosphates. This is AZTTP. And it can be added to the chain since the 5' end is normal. All right? So this guy, you can add him to the chain just as if it was a regular nucleotide. This guy attaches on. And so what you'd get, next step, you get a situation like this. You got your 5' P, oops, sugar, phosphate, sugar, phosphate, sugar. Actually, I'll add that in color in a second. And down here you got 3', sugar, phosphate, sugar. Try to line these up. Sorry, sugar. We got 2, 3, 4. Phosphate, sugar, 5' end. And here we've got U, C, A, C, A, G. All right, here we go. Sorry, I got a little lost in what I was thinking about. You've now added this thing. All right, here we go. So this is the DNA. And this is the RNA. So as far as everything's concerned, this looks normal. We just added the next base was a T. The next base we're going to add is a G, right? That would be the next base that would try to come along. But there's a problem. When that G comes along with its OH and its G here and its 3 phosphates, you have a problem. That is, you can't, no reaction. You can't add the next base to the chain. So there's a bunch of pieces to that I want to, let me put the hydrogen bonds in here. So there's a hydrogen bond, hydrogen bond. So how do all these polymerizing things work? You base pair and add. So how did this get here? The G base paired and then it got stuck on. And then next, the T base pairs and then it gets joined to the chain. Then you're expecting to add a G, et cetera, et cetera. So that's how the chain would grow. AZT, reverse transcriptase doesn't know any better. It adds it to the chain. It looks like a T. It base pairs. It has a 5' end with some phosphates on it. I can glue it into the chain. It glues it into the chain. But now when it goes to add this would be fine, except when you go to add the next base, the enzyme is expecting an OH here, so it can covalently bond. It's not an OH anymore, it's an N3. And you'll have to, when you take organic chemistry, you'd know why. You have to take my word for it. That cannot make a bond to a phosphate. So the chain stops here. It cannot grow any longer. And so if there was a lot more to copy, or even if that base, doesn't even matter if there's a lot more, if that base is important, it's never going to get copied. So what happens is that the virus's genome isn't as long as it should be. It's going to be missing some genes. After that first T where one of these AZTs goes in, you can't make the chain any longer. So that the genome copy is going to be much shorter. It's not going to have all the genes it needs. That's going to be a dud virus. Questions about that? Because there's sort of a lot of pieces to that before I talk about... actually, let me write that up. So therefore, the chain ends here. Or that, in this case, it's the DNA. Chain ends here. Therefore, incomplete virus genome is made. Therefore, the virus can't replicate. So if you remember the stages of HIV infection in a cell, the virus sticks its RNA in, you try to make a DNA copy. This prevents that DNA copy from being made. Basically, you make a useless DNA copy. The cycle of infection stops there, and that cell is not infected. Questions about that? I know there's a lot of pieces there. And all the nucleoside analogs work the same way. They're all missing a 3' OH, no matter how if you look at all the different ones that are out there on the market. And so all of them will be added to a chain, and then they're chain terminators.